So the last prop that we need to add to our world is actually an invisible one, and this is going to be called a force movement zone. Now, essentially what I'm going to do is create a blueprint that whenever there's a ball inside of it, it forces it to only move in one direction. But it does in a kind of subtle way, is the intention here. So I'm going to right click, create a blueprint class, and that's going to be an actor, because we're placing it in the world. And this is going to be called BP underscore force movements zone. So I'm going to double click on the zone, and I'm going to add a component to it. And the component that I'm going to add initially is going to be box collision. So box collision. And this is going to represent the zone with a forced movement direction in it. For the time being, 32 by 32 by 32 is totally fine. However, when I go down to collision, I want to actually set this to custom. I want to basically ignore everything except for one thing, which is physics bodies. So we've told it that it's going to ignore physics bodies, and that should be it for our initial setup here. Now the other thing that I'm going to do is I'm going to add an arrow component, and this arrow component is going to be what we use to make sure that when we're putting it in the world, we know which direction it's facing. So I'm going to add an arrow component, which is just going to look like that. Now, for this, what we need to do is compile, save. I'm actually going to use tick here. Now, there are plenty of ways that you could avoid using tick in this instance. You could set it up so that it only does this when an object goes in, it turns it on, and when an object leaves, it turns it off. But because this is a quick setup, I'm going to set it up through tick. Just be aware that there are slightly more efficient ways that we could ultimately be running this function. And what I'm going to do is off of tick, I'm going to run a for each loop. For each loop. And that's going to cycle through an array. Which array? Get overlapping actors. So get overlapping actors gets all of the certain type of actor that is currently overlapping this actor. So at the moment I'm going to go through and I'm going to look for every single ball that is overlapping this actor. So what we need to do here is we need to get the actor. I'm going to cast it to a ball. Now I know this is going to be a ball. I'm going to convert it to a pure cast because I know it's going to be, since it's the only thing that can come out of that. At which point I'm going to set the physics linear velocity. Okay? So what I'm essentially doing here is I'm setting the velocity of the ball. Now, when I set this, I need to have a velocity to set it to. So, what's that velocity? Here's where a bit of math has to come into things. Essentially what I'm going to do is I'm going to, first off, get the current velocity of the ball. So we're going to have the current velocity of the ball, at which point this velocity is in world space. So if it's moving along X, Y, or Z according to the world, it's X, Y, and Z like in those world coordinates. But if I was to rotate this object, they would no longer match up with one another. So there's an interesting thing we can do here called an inverse transform, which essentially lets us get something and convert it from one space into another space. So what I mean by that is this. If I was to currently get my force movement zone, forward for this object is that arrow. So the x-axis goes along this way. And so it does with the world. But if I was to rotate this, I now have a local x-axis that's going that way, while a world x-axis is going this way. So what I can do is I can get the velocity in world space. I can run an inverse transform on it. So inverse transform the direction. And now it's going to ask me, when I add this, it's going to say, well, if you're adding an inverse transform, which object do you want it to now match? So this is converting from world space into something else. And the easiest thing for me to do there is to get the arrow, because we know that that's the direction that we always want to face, get the world transform of the arrow, and convert it into the arrow's space rather than in world space. From here, what we've essentially done is we're now getting a speed value relative to the force volume that we've just created, which lets us do some pretty cool stuff. In this case, what it lets me do is run a function to basically interpolate the velocity from its current velocity into the desired velocity. And the desired velocity is actually rather simple. The desired velocity is a maximum x value that we're going to give it, or its current x value as long as it's greater than 0. So we're going to have like a minimum and a maximum clamped on the x, while the y and z we don't really care about. I'll show you what I mean by that. So if this is the direction, if I was to break this direction, we've now got an x, y, and z value out of this, which are all relative to myself. What I'm going to do here is I'm going to tell it that ultimately the speed that we want to have is going to be, if we're moving below 800 units along the x-axis, I want you to move towards 800. Otherwise, I want to use a max value of a very high number. I'm just going to set this to 19,000. I could have used a min here, but I'm just going to set it up this way for simplicity, since you're familiar with clamps already. Now, you're probably sitting there going, well, if I was to just set this as my x, y, and z axes, wouldn't that create a problem? And you'd be right, because that would instantaneously set my speed to be this speed. However, if I was to use what's called a vinterp2, what this does is my current speed is this, my target speed is this, and the maximum amount of change I'm allowed to make per second is this. So I can actually set this up as the target speed. So I'm going to split the struct and tell it that the x speed is this one that we just gave it. Y and z are both 0. The current speed is going to be this, because we know we've already gotten this speed. And then finally, just before plugging it in, I actually don't want to connect that. What I want to do instead is now transform it back into world space. So I'm going to, once again, get the arrows world transform. And if I drag off of this, instead of doing an inverse transform, I'm going to do a transform direction, which is essentially going to go, hey, this is the current space that I'm in, remove that, and it'll put you into world coordinates. Now, this is a very cheeky way to do what we're doing here, but it will work, and I'll demonstrate how this functions. The most obvious thing that could make this go wrong is if the ball wasn't set to be a physics actor, but I've just gone through and just double checked, because out of paranoia, the ball's collision is definitely set to be a physics body. So we're all fine on that front. So I'm going to drag a force speed volume into the map. The quickest way for me to test this is to actually put it in here so that I can see that it's working. So if I drop this in here and I was to point this way, we can see that this is now encompassing this entire area. Before I hit play though, I just remembered I've made another mistake. I'm going to go back to my force speed volume. I got a little eager when I added this. I forgot to set delta time or interp speed. That was a good trick. So I'm going to say the interp speed, just going to set it to 100. And delta, I'm just going to say get the world delta. So remember, delta is the time between ticks for this object. Compile, save, and this should now function. Good thing I caught that before hitting play. Now if I hit play, you can see the object is now bouncing into that zone and getting some speed as it shoots back. Now the amount of relaxation that we want to put on that is totally controllable. If I set this interp speed to be 20 instead, and hit play, it's a little bit less. Interp speed, and I set it all the way just down to 1. So that wasn't enough. So a good idea here is to actually promote this to a variable that can be set on your own asset. So I'm going to call this the adoption speed, for lack of a better word. And the default value of adoption speed is just going to be set, let's try 15 or 20. 15 sounds good. Compile, save, play, play. I saw I got that initial burst as it dropped into it, and that was about what I wanted. Now a good area of use for this is I know I always want a ball that's coming through here to go out that direction. So if I was to get this, pop it up to here, rotate it to there, and now I'm going to shrink it back down a bit. Any ball coming up into this area is now going to go through this area and pop through that. I might thin this out just a little bit as well so that we don't force the balls into the edges of that. But this should work. So that went straight through, and we should be all good. So with that, we have essentially the last prop. It's time for us to now start looking at the last game function, which is the tilt function, and from there we can then move on to aesthetics, and this project will be complete. So let's move on to the tilt function.